Slideshow. That's it.
Okay. As you've already gathered, each of us owns a package of work, and we're presenting slides of other partners. So, as has already been said,
Did you notice that, by the way? Obviously, we could have done all that, so
No.
it is sometimes quite uncomfortable to present these slides.
it's interesting, let's put it that way. So hopefully there's people in the audience that can help me with the difficult questions. What I'm going to talk a bit about is sensors, NDT and metrology. Now, this is a lightning fast skip through. In 4.5 years, a lot of things have happened. This is giving you flavours only, and there's people here you can talk to in the breaks about getting more detail. It's just giving you ideas of what's been done and what we've achieved. So, what did we set out with the objectives? Well, we wanted to increase the use of Adaptronics, in-situ sensing, in-process feedback and control, and investigate new techniques for in-situ sensing, pyrometry, piezoelectrics, electric signals, which provides real-time information to allow you to do something as the build's progressing. So you don't get to the end and then find out there's a problem. We want to try and maintain some level of control, or indeed just to switch the build off and say, this isn't good enough, without wasting things. And also part of this was how to investigate the parts after they're made. As David and some of the diagrams you've seen, they're complex parts. They're not easy to investigate. They're not easy to see what's happening in those parts without tearing them to pieces. So it's seeing what we could do to improve that situation. Now, where did we start? Well, started, 5 years ago with writing a proposal. 4.5 years ago, when we wrote it, it was, we had some machines, and most of the machines were running blind. Very little sensing. And you make a part, and then you decide and find out if it's good enough, and you iterate it. That's still the case to some degree, but things have now moved forward. An NDT inspection of AM parts is difficult due to that complexity. You've seen some of the brackets, and there's a sun sensor, which you'll hear a bit more about this afternoon. These things are complex, they're harder, they're not simple things we're talking about. So what we wanted to try and do was move that forward, put more process monitoring in place, and improve the inspection technologies without tearing things to pieces. So I'm going to talk in two parts. First about sensors, and then a bit about metrology and NDT. Now, to give a flavour, we don't have one technology in this, as you've heard. We have multiple technologies. We've had wire and arc. We had a version of that, rapid plasma deposition from Norse, blown powder. We had laser metal deposition and wire feed systems. And last but not least, laser power bed fusion. Each of those had teams and various teams, multiple teams working them to drive them forward. I'm going to touch on each of them very briefly just to give you a flavour. So first of all, Technalia and wire arc. Well, as you probably know, this is a combination of electric arc and some wire. And basically, on the system that you can see on the right here, they implemented a set of in-situ sensors. That's pyrometry, laser scanner, oxygen meter, and looked at internal signals. That's voltage, intensity, feed rate, to try and get a handle on what the machine was doing and offer some level of control. And in particular, you have to know where you are. You have to know where you are with the torch relative to the piece part, and also the feed rate. So it's monitoring all these things to try and control it in some way. So what did they do? And Technalia, jump in on me if you want to add anything. Just some examples here. So there's a part on the left here, and some of the signals. Voltage, you can look at these. You can look at the higher voltage values in the crosses. That tells you something about what's going on as you build the part. You've got to know where you are. So you've got to have very good positioning and know where the torch is, know where the part is, and know what the geometry you're building. And that's the height control. And if you put height control in place from some of the parameters, you can start to model and look at the growth of the part, the melt pool, and some of the dynamics in there, and try and get some information. This all fed together, and basically this has come together certainly for steel, but some of the mechanisms and controls you've got in here are not quite as easy for titanium, mostly because it burns a lot brighter. But the basic elements of the system are there to allow you to start looking at this and trying to relate the mechanical outcome to the monitoring that you're doing. One of the things that Dave has already alluded to was we tried to look at new mechanisms to control the the growth of the grains and how the structure of the parts were created. So some vibration stimuli were put in basically in two areas, one of which was a device in about 170 hertz, a pneumatic actuator, and the second one was ultrasonic image frequency about 20 kilohertz, to try and see what would happen. Now in general, what you have is that the commoner grains created in the melt zone could be detrimental for the mechanical properties. So you want to try and change that. And this was an attempt to say, if we did something, agitate the melt pool, what can we improve or what can we do? You looked at this in terms of a high-speed camera. So, a bit of a heavy slide. The images at the top are builds. They're really vertical, but they're easy to put them on the slide this way. Now, the vibration device was effective to generate agitation in the melt pool, but you could drive it too far. It could be detrimental. If you have too much actuation in the pneumatics, then the melt pool becomes unstable and you get nothing out of it. But it is possible to reduce the grain size by inducing vibrations, but the improvement is low. And for big parts, you have difficulties with making sure that the vibration is uniform for the part. The stability of the process, it's not easy to control this and control the effect of it. As already said, the grain size improvement wasn't significant to take this further forward, but we had a look at it to see what we could do. Technalia, if you're here, any comments? Okay. Norsk, rapid plasma deposition, which is a form of WARM. So you have a highly commolated arc, ionized gas, and you have delivery of metal wire feedstock into that melt pool. In order to try and see if they could put some level of control in here, they looked at what's called the interpass temperature, and it's the surface temperature of the workpiece before you put the next layer down. So you look at that and see what it can do. And these systems generally do very high deposition rates and can build up to about 1 meter sized parts. Now, the investigation of this basically showed that you can actually use the interface temperature because it just, lowering the interface temperature basically increases the cooling rates and leads to a better microstructure and a high hardness. You can see that in the table up here. Now that should translate to higher yield strengths. So this is a method that allows them to control and improve the situation. Francois, are you here?
Said it perfectly.
Okay, on to blown powder. Now, Arepa implemented what's called a Pressotech head, which was originally developed for laser welding applications. Now, blown powder in this type of system, they're used to create parts and mend parts. But what the Pressotech head itself has 4 diodes on it, looking at the melt pool, the plasma, the reflected power, and the instant power. And again, this was an attempt to try and control this. But it's not. It's a monitoring system more in order to try and understand and detect when an instability or a problem is arising. So basically, you can then choose what to do. You can choose to change something, or you can change to cancel something, or you can start again and try again. It allows you, without getting to the end, to find that a big part has gone wrong. Now, there are different things you can look at here with these signals, and there's just a couple of graphs here. So you can see height variation within the part, so the distance from the part to the nozzle by looking at the signal. You can actually look at some instabilities. The lack of powder, that basically corresponds to the variations you can see on the left in that second graph are indicative of a collapse of the structure or the collapse of the layers or the lack of powder. Now, this is fairly early days, but you can actually start to get some information and decide what you want to do with it. Now, on top of that, Arepa put in a camera, which is looking at the melt pool. You can see some of the characteristics of the camera here, in terms of its size. And with this, you can start to look at the melt pool. You can look at some of the dynamics. You can look at the melt pool length, the axis, the geometry, the evolution. And this camera allows you to see if there's some level of impurity or there's some overheating, if there's some areas of the melt pool that are are separating out. Now again, you can start to think about this. Now the problem with this is you get a lot of data coming out of this. So handling that real time, managing it real time, and doing something about it is really the next challenge. There's a lot there, there's a lot of information you can play with, but what do you do? Moving on to LMD. It's a generative process where you basically can repair parts. And in here, what you've got is a head, which is firing onto an APOD 10, a Trump hybrid part. And you've got a laser line scanner, a sensor, which can look at points on that built surface. And basically what you do is you put a layer down, then you switch the scanner out the way or the build out the way, and you move the laser line scanner in and look at that surface. And on the right there, you can see the principle of it, which is basically you've got a measurement of what has happened and a correction that you can apply if you need to. That's arisen from the data between what you're actually doing on the head and what you're getting from the laser line scanner. Now this is actually in place, I think, on 3 machines, one at Birmingham, one at Trump, and actually a 5-axis mill at BCT. And it's a combination of BCT software and Trump hardware. And that's a lot of the work we've done here is collaborative in nature. It's not just one group, it's many groups pooling their knowledge together to create something a bit better.
Probably worth mentioning, you wouldn't have to necessarily measure every layer.
No, you don't.
It's a way of making sure you're keeping track of what you're doing and adaptively dealing with it in the CAD system.
Yep. Again, it's got the ability to generate an awful lot of data. And it's what you do, what you choose to do with it. Do you do every 10? And again, it comes down to part geometry. Not one decision for one part is not the same decision for another part. Airbus, they have a wire feed laser system where they're a lateral wire feed. And what they've been doing is building some sample parts here and micro-sectioning them for this particular system and having a look at what it does. And basically you get very good density, you get very small pores at the end of order of 10 microns. And they can actually be closed up with HIP to the order of a few microns. So they're fairly pleased with this as a process that they're using. And a bit more in terms of the outcome of this. When you do build for some of these tools, you do get anisotropy. You get different properties coming out in different directions depending how you look at the parts that you section. So for example, for this particular tool, specimens built in the Z direction don't reach the strength values nor the elongation values. But in the X direction, they do. So when you're designing the part and you're looking at that orientation and you're looking at the supports, you have to consider what the tool is doing for you, what its result is, to get the best out of it. In terms of, we had to look at fracture toughness. Now this was a bit more negative. We did have a look, but unfortunately the parts that they produced and the parts they looked at in the timescale of AMAZE didn't have kick values in an appropriate range. So they've got to redo this and look at further test specimens. So not everything out of this is green. There are things that we have to improve. There's things that can be taken forward. There's things that can be done better. And particularly for sensors, depending on where you look, it can be early days. For Renishaw, we started to look at the melt pool itself and the light emitting from the light pool, the melt pool, and the dynamics of that. And to see if that can be used to investigate the quality of the melt track and stability of the process, and whether it can be used as an in-process monitoring tool. And if possible, the electron temperature derived from the intensities of the emission could actually give us some useful information. Now, due to the viewing angle of the spectrometer, we had fairly small samples, and we used thin walls as a measurement of this. To cut a very long story short, we couldn't actually directly relate the plasma temperature to the wall thickness, not with this particular setup. Now, to actually take this further, we'd have to look at multiple sensors, multiple regimes, and see if it can give us any more information. But as it was, this told us a route that we didn't want to go down any further. So it's good research to do, but not the way we wanted to go. People have talked a lot about cameras in systems, and for laser powder bed fusion, we've been looking at a camera, and optical cameras are very good for looking at the physical aspects of what's going in the chamber. You can look at wiper damage. You've heard about the wiper moving to put a thin layer of powder down of typically 30, 60 microns thick. So if that gets damaged or the powder doesn't spread evenly, that's something in principle you should be able to see and deal with. And if you can monitor that and automatically pick it up, then you can decide what to do about it. You could relayer, or you could stop, or you could do something. It's about what you use the data for now, as much as acquiring the data. Now, for laser powder bed fusion, the system's a bit harder. You have a chamber, for us, with argon in it, and it's not a very nice environment. It's probably putting it kindly. It's highly reflective, and you get a lot of powder contamination on surfaces. So it's a very complex area to get signals out of with decent signal-to-noise parts, so you can make sense of it. So we started looking, or we've been looking at, ways of using that data and improving the data through contours, snakes, thresholding, and colouring, and basically, for us, very important, extracting straight lines, making sense of what we're seeing through software enhancement and image processing. So putting a camera isn't the end of the story, it's the start of the story. And it can be a long road to get us to the end of that. So that's kind of a whiz through sensors for various technologies. And again, many of the teams are here to dig a bit further if you really want to, or to understand it further. NDT and metrology, moving slightly on, that's the third objective. MTC have done a lot of work in terms of X-ray limits of detection. So Ben, you're going to jump in when I get it wrong. And laser ultrasound, and a new area they're looking at, which is nonlinear acoustics. Norsk, with their WARM-like rapid plasma deposition system, have been using phased array ultrasound, and they've actually done something simple, but is very effective in terms of measuring datums on parts, and I'll talk a bit about that. And a nice bit study, which I will struggle to explain, is applications of XCT with lattices. So I hope you are here. Good. Well, you're up there, though, aren't you?
So that's Manchester. That's Alex at Manchester. Ben, you want to stand up and so people got questions, they can find you at lunch break. And then anybody here from North, you've got?
Yep, Francois over there.
Okay. So Francois over there.
Technalia is up there. So hopefully faces you might remember if you've got questions. So now this is real highlights, the helicopter views. The amount of work that went into this was significant. And as in all of AMAZE, there are numerous pages of reports that have been generated in terms of the detail of what's been done. And some real significant good work has been done in all of these areas, of which we can only give gists of. So for X-ray limits, we had a cut up and we had a look at the an image, and we basically can see on the image in the middle, the elements circled in green are issues or problems, defects that were seen in both the cut up and the XCT, and red are not. And from this analysis, a bit more deeper dive, you can see that the type of X-ray minimum size of the order of 80 microns. And for this particular part, we didn't see anything less than about 132, I think it was, microns. But this was this particular part in this particular geometry. One of the things that we said we'd do was we'd take some of the APOD parts, and this is APOD 2, which people already talked about, and look at them in terms of the metrology. There's a lot of bits of data in here. What we did was not only look at the part as built, but we looked at it as we went through the process. So as it was built, then it was hit, then it may be machined. So we looked at the metrology as it changed all the way through. And in particular, the metrology comparison between as-built and HIPT came out about 0.11 millimeters. And again, there's a lot more data behind this, but it gives you an idea of the kind of things that we were doing. One of the things that people take for granted is that when you put a part on a metrology machine, you automatically assume that you're going to get the same results every time you do it. You don't. And it is dependent on machine. So one of the things that MTC did was to look at the three machines here, Nikon, the GOM, and the Hexagon, with tactile probes and saw what repeatability, or what tolerance repeatability there was. And there is variability, and you've got to take that into account. Not everything gives the same information. And in particular, the hexagon with the tactile probe was best, with a repeatability of 3%, and the others go down into 11 and 19%. So you've got to be cautious in what you measure. You can measure it as long as you know what your interpretation of those results actually are. MTC looked at laser ultrasound. Now, laser ultrasound, I'm sure many of you are aware, is you generate an ultrasonic wave by shining a pulsed laser on a part, and then you use a secondary laser to detect waveform disturbances, particularly from the Rayleigh surface wave, which interacts with the defects and the issues inside the parts. And this particular diagram here shows a block that was pre-machined. It doesn't come up very easily, but different sized holes along the sides of the block. And you can see some disturbances in the B scan. And you can see holes of the order 0.3 to 0.8 millimeters. Again, a lot of work has been done on this. This is a highlight to give you a taste, and Ben, I'm sure, will talk at length on it if you ask him. I'm getting to the end of it, a couple more slides. Laser ultrasound, we've been looking at on laser powered bed fusion voids. We've actually been looking at actual parts to prove this isn't a piece part that we've drilled something in so we know what we're looking for. We've gone to look for things. And on older parts, we've seen voids. So this shows you the proof that you can go. Now, the difficulty is it's the scan area, where you look, how you look. So there are improvements that you have to look for, but there's the basis there that you can start to say this tool can be used. Now, a new one is nonlinear acoustics, and Theta Tech are outside, can talk a lot more about this than I can, but very early study on this is showing that we can detect good and bad signatures, different signatures from the APOD 2, older APOD 2 parts. A very early study, but again, for non-invasive testing, it looks promising. I think that's yours, Ben. Is there anything you want to add?
No, that's fine. And this place is here too, so last question. You want to start up? You'll be...
We'll be out there later.
Outside.
Okay. So Norsk have used phased array ultrasonic inspection, conventional ultrasonic regularly, and they've actually used a handheld machine. It's quite impressive when you see that the first time. When you're holding this machine and you get a full 3D image out of it. Very, very nice piece of kit. And it shows using these tools you can get down to look at 1.1, 1.4 millimeter defects. So it's a good tool to use. And it doesn't have to be complex. It doesn't have to be big. It doesn't have to be smart. You've got to choose the tool that's appropriate for the piece you're looking at in terms of how big you're making it. You know, laser powered bed fusion has, you're creating things of the order of tens of microns, different processes and different scales, so you can choose different measuring methods. And something that I think is clever, and it's fairly obvious, is that when you create a part, a preform, everyone who looks at that part has to look at it in the same way, with the same datums. Or you can end up getting data back that is meaningless. And what Norsk have done is not just implemented this internally, they've implemented this through the whole of their supply chain. So when they create a preform or create a part, that everyone knows what they're talking about and can reference back to it. Francois, do you want to add?
The idea is to use a common reference frame from the point where the part is deposited to the point where it's machined. And this avoids the risk of non-cleanup surfaces.
Now this is the one I'm going to struggle a bit with. Manchester have done a lot of studies of applications of XCT in parts, and for the top left diagram here is a study looking at the internal structure of powder particles in terms of their morphology and internal defects. And again, I think they can explain a lot more about this. And I think you've already presented on this before, my one, haven't you? Yeah. So those who missed that, please tackle them later. Top left reveals the internal structure of powder particles. Top right reveals the new phenomena in basically looking at laser matter interaction. Bottom left, characteristics of preheating conditions. You can look at sintering and the effects of sintering. And bottom right, something that David showed in a single slide a bit earlier, is looking at the characterizing the failure mechanism of auxetic lattices under compression. A lot of work in here, a lot of complex work, so I'm not going to attempt to even do better than that, I think, at the moment. And last but not least, again from Manchester, they've been looking at lattices and struts. And in diagrams A to C, they've been looking at lattice structures using 3 different processing parameters. And then looking in item D, bottom left, looking at the internal pores in lattice structure, and then looking at the basic building blocks of lattice structures in terms of what's called maximum inscribed spheres. And all this allows them to feed back to the collaborators when they're creating these lattices in terms of what's good, what's bad, what they should avoid, and what they can and can't do. Now that's really high level, touchy-feely. There's a lot of teams that contributed. You've already had people standing up, so I won't go through it again. But a lot of processes, a lot of teams, a lot of work over a lot of years. I think that's it.
Thank you. Any questions for Stuart?
Say no questions. Up the top.
This makes a small addition to that. So I'm from Birmingham. We worked a lot with BCT, really coming up with the algorithm for the process control. It works really well. If you want to build a shape without having to get a really optimized program in advance, the control system does a great job of making it work.
Thank you. Anything else?